Okay, let's kick things off with a totally staggering number. $1 billion. In the traditional auto industry, if you want to redesign a gas-powered car's wheelbase by just 6 inches, it can literally cost up to $1 billion. Oh, and it takes 5 to 8 years of development to pull off. It's this massive ripple effect, right? You change the wheelbase, and suddenly you have to redesign half the transmission shaft, completely recalculate the center of gravity, and engineer entirely new suspension systems from scratch. So that begs the question, how exactly do EVs fix this billion-dollar problem? Well, this incredible engineering bottleneck is exactly what modern electric vehicles are solving in a just beautifully elegant way. By completely reimagining the physical foundation of the car itself, EV manufacturers are cutting out these massive costs and insane development timelines entirely. Welcome to this explainer. Today, we're going to dissect the modern electric vehicle from the outside in. We're going to treat the EV like a living, breathing organism to understand exactly how it works, how all its internal systems interact, and why this represents an absolutely monumental shift in engineering. Here's our blueprint for today. 1. The skateboard chassis revolution. 2. Meet the powertrain organs. 3. Inside the lithium-ion heart. 4. The thermal juggling act. And 5. Sustainable and modular futures. All right, let's dive right in.
Section 1. The skateboard chassis revolution.
Now, the skateboard chassis isn't actually a brand new idea. It's evolved over 20 years. It really started way back with the 2002 General Motors autonomy concept and then the 2003 high-wire proof of concept. Over the years, that idea matured into a commercial reality with platforms like the 2018 Audi e-tron. And now we're seeing highly flexible, open-source platforms today, like Foxconn's MIH in 2024. What's super interesting here is how this skeleton actually functions. By housing the battery pack and the motors in a completely flat floor, it dramatically lowers the vehicle's center of gravity. Plus, it relies on drive-by-wire electronic controls. That means absolutely no mechanical steering columns or brake linkages getting in your way. And because of that, you can build pretty much anything, from a sleek sports car to a heavy-duty delivery truck, on the exact same base, just by swapping out the modular bodywork on top. It's like a giant Lego set. Section 2. Meet the powertrain organs. Inside the electric power control unit, we have the VCU, which is arguably the most important organ of the bunch. Think of the VCU as the brain of the car. It acts as a control tower, making constant split-second decisions. It oversees motor control, manages exactly how aggressively your car uses regenerative braking to recapture energy, and even balances the load of your air conditioning so the vehicle always operates at peak efficiency. Meanwhile, we have the LDC, which acts as a crucial translator for the system. See, your main battery pack operates at hundreds of volts, which is way too much for your dashboard displays or your headlights. So the LDC safely steps down that massive high-voltage electricity into a standard 12-volt low-voltage current. That's what powers all those everyday electronics you rely on while driving. So, how does all this translate into physical movement? Well, when we compare the EV's reducer to a traditional multi-gear transmission, the contrast is beautifully simple. A traditional gas engine has to constantly shift through multiple gears to match the engine's RPM to your driving speed. But electric motors, they spin at incredibly high speeds natively. So the EV reducer's sole job is just to dial down that high RPM to give the car massive immediate torque right at the wheels. No complex gear shifts required at all. Section 3. Inside the lithium-ion heart. The battery actually breathes energy in a fascinating two-step chemical cycle. When you're driving, which is the discharging phase, lithium ions flow from the cathode, pass straight through a liquid electrolyte and a micropermeable separator, and finally settle in the anode. That flow is what generates the electricity to move the car. Then, when you plug the car in or hit the brakes for regenerative braking, that exact chemical reaction reverses itself, sending the ions right back to the cathode for storage. And what's really wild is the kind of longevity this controlled chemical breathing creates. People are always worrying about battery degradation, right? But let's look at the actual math. If a 64 kilowatt-hour battery is driven 77 kilometers a day, which is only about 20% of its max range, and it's recharged efficiently every night, it could theoretically last for 8,000 charge cycles. Put that into perspective, that translates to an incredible 22 years of usability.
Section 4. The thermal juggling act.
Now, here's a pretty crucial vulnerability we need to talk about. Extreme cold weather can reduce an EV's driving range by nearly 60%. Why is that? Well, unlike gas cars, EVs don't have a hot engine constantly generating waste heat that you can use to warm the cabin. In a basic EV, heating the cabin means turning on an electric heater that drains the main battery directly. So in freezing weather, your driving range gets absolutely slashed. To fix this and achieve perfect thermal homeostasis, modern EVs rely on a highly advanced heat pump architecture. We're talking about 3 distinct interconnected fluid loops here: the cabin air loop, a refrigerant loop, and a reconfigurable dual coolant circuit. By linking all these together, the system can actually scavenge waste heat from the motors and the power electronics, and then cleverly route it to warm up both the sensitive battery pack and the human passengers inside. A huge piece of that puzzle is the dedicated battery coolant pump. This is an essential little component tasked with circulating fluid for one reason only: keeping the battery cells in their perfect Goldilocks temperature window. Because if those cells get too cold, they can't charge efficiently, and if they get too hot, they start to degrade. At the exact same time, there's a completely separate motor loop pump regulating the powertrain. Now, the brilliant part is that advanced directional valves can actually link these 2 loops, the battery loop and the motor loop, together. When the weather gets freezing cold, they shift into series, effectively sharing the heat generated by the spinning motor to warm up the battery block. Distilling all the intense math down, engineers coordinate this massive juggling act using advanced software called Nonlinear Model Predictive Control, or NMPC. It acts like a highly intelligent predictive thermostat. It's constantly anticipating conditions and coordinating all the pumps, compressors, and valves simultaneously. This software alone can reduce the vehicle's thermal energy consumption by 20 to 28%, which preserves your battery for what it's meant for: actual driving.
Section 5. Sustainable and Modular Futures.
To keep EV manufacturing sustainable for the long haul, the industry is heavily investing in a process called destructive dismantling. Essentially, this recovers valuable elements like lithium, nickel, and cobalt from old batteries. As the U.S. Department of Energy points out, this recycled material could provide a massive 1/3 of domestic cathode material needs by the year 2030, which would drastically reduce our need for new mining. We're also seeing some truly incredible physical evolutions in the vehicle's anatomy. Companies are currently developing things like RE corner technology, which literally crams all the powertrain organs, the motors, steering, and brakes, directly into the wheel arches to free up maximum space. We're also seeing the rise of solid-state batteries. These replace the liquid electrolyte with solid materials that simply don't leak, are much safer, and hold drastically more energy. And that brings us to the ultimate evolution: structural batteries. Structural batteries take this solid-state tech and use it to form the physical frame of the car itself. So I want to leave you with this thought today. When the car's body panels, its doors, roof, and chassis, actually are the batteries storing the energy, how is that going to change the way we view, repair, and recycle cars forever? It completely blurs the line between the skeleton and the heart, and honestly, it just might change the future of mobility for good. Thanks so much for joining me on this explainer, and I'll catch you next time.